At the heart of the HFPTD is the Vacuum Index Modulation Lattice. This structure consists of metamaterial honeycomb cells, each embedded with quantum permittivity actuators. These actuators can shift the local vacuum index in discrete, high-contrast steps, enabling rapid transitions between different electromagnetic boundary conditions. The modulation occurs at macroflash rates of 220 Hz, with internal microstructure operating at much higher frequencies. This dynamic control over the vacuum index is what allows the HFPTD to generate thrust without expelling mass, setting it apart from conventional propulsion systems. The HFPTD's propulsion is governed by an asymmetric duty cycle. During the short, bright on phase, the toroidal ring enters a high coupling state, strongly interacting with the vacuum and ambient photon field. In the longer, dark off phase, the ring decouples, coasting in a locally altered metric bubble. The imbalance between these phases produces a net thrust, analogous to a rectified, time-varying Casimir-like interaction. By precisely controlling the duty cycle, the craft can optimize thrust and efficiency, achieving velocities far beyond traditional drives. Steering the HFPTD is accomplished through the phase tilt vectoring ring. Around the toroidal disk, segments are phase controlled so that the leading edge enters the high coupling state slightly before the trailing edge. This creates a traveling wave of vacuum index modulation, effectively pushing the craft along a chosen vector. The phase gradient around the ring determines the direction and magnitude of thrust, allowing for precise maneuvering and even instantaneous changes in direction. The vacuum rectification chamber is a central feature of the HFPTD, converting oscillatory field interactions into linear momentum. Alternating layers within the chamber create standing waves of electromagnetic energy, which are rectified to produce a net pressure gradient. This process is key to the drive's ability to generate thrust without reaction mass, leveraging the engineered properties of the vacuum itself. A defining feature of the HFPTD is its ability to form a translation bubble, a region of altered vacuum index that reduces inertial coupling. This bubble allows the craft to achieve extreme accelerations and velocities, with the boundary layer precisely controlled for stability. The translation bubble is not a traditional warp field, but a localized metric envelope, engineered for both speed and safety. Efficiency is paramount in the HFPTD's design. The system employs a closed-loop energy recycling architecture with vacuum energy interfaces and zero-loss capacitors, ensuring that nearly all input energy is reused. This allows for sustained operation without the need for external fuel or frequent recharging, making the HFPTD ideal for long-duration missions in deep space or on planetary surfaces. The structural integrity of the HFPTD is ensured by a robust toroidal hull, reinforced with radial ribs and shear transfer webs. Stress paths are carefully mapped and managed, with flex relief segments and torsional reinforcement bands absorbing dynamic loads during high acceleration maneuvers. The hull's advanced composite materials provide both strength and electromagnetic neutrality, critical for maintaining field stability. Navigation in the HFPTD is achieved by manipulating the phase gradient around the toroidal ring. By adjusting the timing of flash phase nodes, the craft can steer along any vector, including instantaneous reversals. The navigation matrix translates desired velocity changes into precise phase adjustments, allowing for agile and responsive control in any environment. The HFPTD's operation is characterized by distinctive telemetry signatures, flash phase pulses at 20 Hz with duty cycles as low as 1% create a unique waveform that can be monitored for diagnostic and fleet coordination purposes. These telemetry signals are essential for maintaining synchronization across multiple craft and for verifying system health during operation. Sightings of HFPTD-like craft have been correlated with specific observational signatures such as synchronous brightness, modulation, and extreme velocities. By overlaying flash phase timing data on maps of Earth and the Moon, Analysts can track trajectories and validate the presence of HFPTD-equipped vehicles. This correlation supports the authenticity and operational capabilities of the system. The HFPTD stands as a testament to James Edward Hartman's pioneering work in advanced propulsion. By integrating duty cycle-driven thrust, phase tilt steering, and vacuum rectification, the HFPTD establishes a new class of field interaction drives. Its legacy is not only in its technical achievements, but also in its influence on future propulsion research and aerospace engineering. The HFPTD's operation is grounded in rigorous mathematics. The duty cycle thrust equation relates flash and dark durations to net thrust, while the phase tilt steering equation defines how phase gradients translate to directional control. The translation bubble's metric index is calculated to ensure inertial reduction, and all parameters are optimized for maximum efficiency and safety. These equations form the backbone of the HFPTD's control algorithms and operational protocols. Each subsystem of the HFPTD is engineered for precision and reliability. The toroidal vacuum index modulation lattice, flash phase emissive nodes, and phase tilt vectoring ring all work in concert to produce controlled thrust and maneuverability. Engineering parameters such as cell size, modulation frequency, and actuator alignment are tightly specified, ensuring consistent performance across all operational scenarios. Maintaining the stability of the translation bubble is critical for safe and effective operation. The bubble forms when the vacuum index shift exceeds a specific threshold, reducing inertia and drag. Stability is monitored by tracking the rate of change in the vacuum index. If this rate exceeds allowable limits, the bubble may collapse, potentially leading to structural failure. Continuous monitoring and calibration are essential to ensure bubble integrity during high-speed maneuvers. The HFPTD's navigation system translates pilot inputs into phase gradient adjustments around the toroidal ring. By manipulating the timing of flash phase nodes, the craft can execute complex maneuvers, including instantaneous reversals and agile vector changes. The navigation matrix ensures that all movements are precisely coordinated, maintaining stability and synchronization with fleet operations. Powering the HFPTD is a zero-loss field recycling loop, interfacing directly with the vacuum energy field. The system's efficiency approaches 99.9999%, with nearly all input energy recycled through the flash phase power distributor and lattice modulation driver. This closed-loop architecture ensures sustained operation and minimal energy loss, supporting both propulsion and auxiliary systems. Routine, maintenance, and calibration are vital for the HFPTD's longevity and performance. Procedures include checking vacuum index uniformity, adjusting actuator timing, verifying phase tilt alignment, and running diagnostics on flash phase nodes. Bubble stability tests ensure that the translation bubble remains within safe parameters, preventing catastrophic failures during operation. Safety is a top priority in the HFPTD's design. Maximum safe acceleration is capped at 500 G, with strict protocols to prevent bubble collapse and flash overload. If the translation bubble collapses at high speed, the craft re-enters normal inertia, risking structural failure. Flash phase nodes are protected against overloads exceeding 108 joules, ensuring operational integrity under all conditions. The HFPTD's performance is characterized by velocity and steering response curves. Velocity increases as the duty cycle decreases, with lower duty cycles enabling higher speed. Steering response is directly proportional to the phase gradient, allowing for sharp turns and agile maneuvers. These curves are essential for mission planning and real-time control adjustments. The HFPTD's engineering drawing pack includes detailed orthographic layouts, metamaterial lattice cell details, flash phase emitter node schematics, and phase tilt steering grids. Each plate is meticulously labeled with revision codes, title blocks, and dimensional tolerances specified for manufacturing. This documentation ensures that every aspect of the HFPTD can be faithfully reproduced and maintained. Precision is critical in the HFPTD's fabrication. Dimensional tolerances are specified for all critical geometry, including outer and inner diameters, disk thickness, and toroidal radius. Fit classes, flatness, concentricity, and symmetry requirements are rigorously defined, ensuring that each component meets the highest standards of aerospace engineering. The metamaterial lattice is fabricated using nano-layer deposition, ion beam etching, and micro-robotic placement of quantum permittivity actuators. Each layer is calibrated for vacuum index uniformity with defect tolerances and purity requirements strictly enforced. This ensures that the lattice performs reliably under all operational conditions. Flash phase nodes are integrated using diamond bit micromachining and femtosecond laser cavity shaping. Each node is calibrated for timing and phase alignment with pulse shaping chambers polished to nanometer level smoothness. This meticulous process ensures that the flash phase system operates with minimal jitter and maximum efficiency. The phase tilt steering grid is installed by positioning phase shift ceramic panels and overlaying a gold graphene mesh. Gradient calibration is performed to ensure linearity and minimal deviation, enabling precise control of the steering wavefront. This subsystem is crucial for agile maneuvering and coordinated fleet operations. The adaptive Albedo cloaking skin is applied using multi-layer optical metamaterial deposition and nano-shutter array installation. Each layer is tested for reflectivity and color matching accuracy, ensuring that the craft can achieve near invisibility during operations. This subsystem is vital for stealth and mission security. The control and navigation core is installed at the heart of the HFPTD. This includes the navigation computer, phase gradient unit, and duty cycle engine. Each module is aligned and connected to the timing buses, with diagnostic loopbacks ensuring system integrity. This core orchestrates all propulsion and navigation functions. Activating the translation bubble involves a two-step process: low power formation and full power stabilization. The vacuum index modulation is gradually increased, with bubble radius and boundary thickness measured and adjusted for symmetry. Once stabilized, the bubble parameters are locked, ensuring safe and efficient operation. The HFPTD's materials are classified into structural, metamaterial, quantum active, and cloaking categories. Each material is defined by its composition, properties, and purity requirements. From titanium vanadium superalloys to adaptive optical metamaterials, every component is engineered for maximum performance and stability under extreme conditions. All materials used in the HFPTD are selected for stability across a wide range of thermal, electromagnetic, and vacuum conditions. Thermal stability ranges from -200 degrees Celsius to plus 1,800 degrees Celsius with zero ferromagnetic response and minimal outgassing. These properties ensure that the craft remains operational and reliable in the harshest environments. Assembly of the HFPTD takes place in a class 1-0 cleanroom within an EM-neutral, vacuum-compatible environment. Temperature is maintained within plus or minus 0.05 degrees Celsius, and all personnel are certified in non-ferromagnetic tool handling and phase alignment procedures. This controlled environment is essential for maintaining the precision and integrity of the craft during assembly. The primary hull assembly begins with the installation of the toroidal spine, followed by radial ribs and shear transfer webs. Each component is bonded and aligned to strict tolerances, with ultrasonic weld integrity scans and structural load simulations performed at every stage. This ensures a robust and reliable foundation for the entire propulsion system. Metamaterial cells are inserted into the hull cavity, with quantum permittivity actuators placed using micro-robotic arms. Control buses are connected, and vacuum index uniformity scans are performed to ensure consistent performance. The lattice is then sealed under EM neutral conditions, completing this critical subsystem. After installation, flash phase nodes are calibrated for pulse, amplitude, duration, and synchronization. A 20 Hz flash phase test is conducted with timing, jitter, and duty cycle deviations measured and corrected. This ensures that the flash phase system operates within specified tolerances for optimal thrust generation. Phase gradient calibration is performed by applying controlled phase tilts and measuring the resulting steering vectors. Deviations are corrected to within 0.5%, ensuring that the craft can execute precise maneuvers. This calibration is essential for both solo and fleet operations, maintaining alignment across all phase tilt nodes. Before deployment, the HFPTD undergoes a series of final acceptance tests. These include torsional load tests, flex segment deformation checks, flash phase operation at full frequency, and translation bubble stability assessments. Only after passing all tests is the craft cleared for operational use, ensuring the highest standards of safety and performance. All materials used in the HFPTD must meet stringent purity and defect tolerance standards. Metals must be at least 99.999% pure. Ceramics must have minimal voids, and metamaterial layers must maintain uniformity within 0.5%. No microcracks or EM active inclusions are permitted, ensuring the longevity and reliability of the craft. Assembly and integration of the HFPTD require a specialized crew, including a chief integration engineer, quantum systems technicians, metamaterial fabrication specialists, and a structural assembly lead. Each role is critical, with responsibilities ranging from phase alignment calibration to structural bonding and diagnostic testing. Proper training and certification are mandatory for all personnel. Safety interlocks and lockout procedures are implemented throughout the assembly and operational phases. These include EM field isolation, vacuum chamber lockouts, and phase alignment safety checks. All procedures are designed to prevent accidental activation or system failures, protecting both the crew and the craft. The Hartman flash phase toroidal translation drive represents a leap forward in propulsion technology. Its unique combination of field interaction physics, advanced materials, and precision engineering sets a new standard for aerospace innovation. As research continues, the HFPTD will inspire future generations of engineers and scientists, paving the way for new discoveries and applications in both space and terrestrial transportation.